Hey everyone, in this video we're going to explore one of the most influential and powerful tools in the world of deep learning, convolutional neural networks or CNNs. Convolutional neural networks have revolutionized many fields, particularly computer vision, due to their unparalleled ability to process and analyze visual data. They are the driving force behind advanced technologies like facial recognition systems, self-driving cars, and diagnostic tools in healthcare. The importance and impact of CNNs stem from their exceptional performance in recognizing patterns, shapes, and structures in images, making them invaluable for tasks involving large-scale visual data. ConvNets are quite similar to traditional neural networks. They consist of neurons with learnable weights and biases, where each neuron takes some inputs, computes a dot product, and optionally follows it with a nonlinearity, an activation function. The entire network still represents a single differentiable score function, transforming raw image pixels at the input layer into class scores at the output layer. Additionally, CNNs have a loss function, like softmax, on the last fully connected layer, and all the optimization techniques and learning strategies for regular neural networks apply to CNNs as well. So what's different? CNN architectures make the explicit assumption that the input is an image, allowing us to encode specific properties into the architecture. This assumption makes the forward function more efficient and significantly reduces the number of parameters in the network. In this video, we'll be going over an overview of the ConvNet architecture, then ConvNet layers, ConvNet architectures, visualizing what ConvNets learn, and transfer learning. Now first, for an overview of the convolutional neural network architecture, recall regular neural nets. Neural networks receive an input, a single vector, and transform it through a series of hidden layers. Each hidden layer is composed of neurons that are fully connected to all neurons in the previous layer, functioning independently without sharing any connections. The last fully connected layer, called the output layer, represents the class scores in classification tasks. However, regular neural nets don't scale well to full images. For example, in CFAR10, images are 32 by 32 by 3, 32 wide, 32 high, and 3 color channels. So a single fully connected neuron in a first hidden layer of a regular neural network would have 32 by 32 by 3 equals 3072 weights. This might seem manageable, but as we move to larger images, such as 200 times 200 times 3, each neuron would require 120,000 weights. With multiple neurons, the number of parameters quickly becomes impractical, leading to inefficiency and overfitting. Convolutional neural networks address this by taking advantage of the input image's structure and arranging neurons in 3 dimensions, width, height, and depth. Unlike regular neural networks, neurons in a ConvNet layer are connected only to a small region of the previous layer. For instance, the input images in CFAR10 have dimensions 32 by 32 by 3, and neurons in subsequent layers will only be connected to small patches of the previous layer, not the entire image. A typical CNN might start with the convolutional layer that uses 32 filters of size 3 by 3, requiring only 896 parameters, which is 32 filters times 3 by 3 filter size times 3 color channels plus 32 biases. This efficiency continues throughout the network, and by the end of the ConvNet architecture, the final output layer of CFAR10 will have dimensions 1 by 1 by 10, effectively reducing the full image into a single vector of class scores along the depth dimension. A simple ConvNet consists of a sequence of layers, each transforming the input volume into an output volume through a differentiable function. The main layers in ConvNet architectures are the convolutional layer, pooling layer, and fully connected layer, similar to those in regular neural networks. These layers are stacked to form a complete ConvNet architecture. Here's an example architecture. For CFAR10 classification, a simple ConvNet could have the architecture input layer to convolutional layer to ReLU activation to pooling to fully connected. Here's a brief breakdown. The input, which would be 32 by 32 by 3, holds the raw pixel values of the image, which have width 32, height 32, and 3 color channels. The convolutional layer computes outputs of neurons connected to local regions in the input. Using 12 filters might result in a volume of 32 by 32 by 12. The ReLU layer applies an element-wise activation function like max of 0 and x, keeping the volume size unchanged, 32 by 32 by 12. The pooling layer performs downsampling along spatial dimensions, reducing the volume size to 16 by 16 by 12. The fully connected layer, finally, computes class scores, resulting in a volume of 1 by 1 by 10, with each number corresponding to a class score in CFAR 10. ConvNets transform the input image layer by layer, from raw pixel values to final class scores. Some layers, like Conv and FC, contain parameters, weights, and biases that are trained using gradient descent, while others, like ReLU and Pool, perform fixed functions without parameters. Now, to talk about the convolutional layer. The convolutional layer is the core building block of convolutional networks, handling most of the computational load. It consists of a set of learnable features that are small spatially along width and height, but extend through the full depth of the input volume. For instance, a filter in the first layer of a ConvNet might be 5 by 5 by 3, covering 5 by 5 pixels in all 3 color channels. During the forward pass, each filter slides or convolves across the input volume's width and height, computing dot products between the filter's weight and the input at each position. This process creates a 2D activation map, representing the filter's response at each spatial location. Multiple filters in each conv layer result in multiple activation maps, which are stacked to form the output volume. Now for local connectivity. Instead of connecting each neuron to all neurons in the previous layer, as in regular neural networks, conv layers connect each neuron to only a local region of the input volume. This local region is called the receptive field, or filter size. The image here illustrates this concept. The input volume on the left is a 32 by 32 by 3 image. The highlighted region shows a small local region, for example a 5 by 5 by 3 region, resulting in 75 weights and 1 bias, that a neuron in the ConvNet layer connects to. This local connectivity allows each neuron to focus on a small part of the input, making the network more efficient. The image illustrates how convolutional layers process input volumes. Here's how it works. The input volume is the left part of the image, which shows a 32 by 32 by 3 input volume, let's say an image from the CFAR 10 dataset. The highlighted patch in the input volume 5 by 5 by 3 represents the local connectivity of a neuron in the conv layer. Each neuron connects only to a small local region rather than the entire input volume. The right part of the image depicts the output volume produced by the conv layer. This volume is a stack of 2D activation maps generated by different filters. Now to talk about filters and depth slices. Neurons at different depths of the output volume use different filters. For example, if the conv layer has 12 filters, there will be 12 different sets of weights and biases, each producing a separate 2D activation map. Neurons within the same depth slice share the same filter weights and biases. This means that as a filter convolves across the input volume, it applies the same set of weights at each spatial location, ensuring consistent detection of features across the input. Now let's talk about parameter efficiency. Consider an input volume of 32 by 32 by 3 in a fully connected layer. If the next layer has 1000 neurons, each of those neurons would need to connect to every pixel in the input volume. The total number of connections or parameters required would be for each neuron 32 width times 32 height times 3 color channels, which is 3072 weights. For 1000 neurons, this becomes 3,072,000 weights. Additionally, each neuron has one bias term. For 1000 neurons, 1000 biases. The total number of parameters would be 3,072,000 weights plus 1000 biases, which is 3,073,000 parameters. If we increase the number of neurons in the fully connected layer to 10,000, the total number of parameters becomes, for each neuron, 32 width times 32 height times 3 color channels, which is, again, 3072 weights. For 10,000 neurons, 3072 weights times 10,000 neurons plus 10,000 biases equals 30,730,000 parameters. Now consider a conv layer with 12 filters of size 5 by 5 applied to the same input volume. Each filter has a 5 width times 5 height times 3 color channels equals 75 weights. For 12 filters, 75 weights times 12 filters equals 900 weights. Additionally, each filter has one bias term, 12 biases. The total number of parameters is 900 weights plus 12 biases, which is 912 parameters. This demonstrates that a conv layer with 12 filters requires only 912 parameters, which is significantly fewer than the 30 million parameters required for a fully connected layer with 10,000 neurons. Now let's talk about spatial arrangement. 3 hyperparameters control the ConvNet layer's output volume size: depth, stride, and zero padding. The depth of the output volume is the number of filters used. The stride is the step size with which the filters slide over the input volume, and zero padding is padding added around the input volume's border to control the spatial size of the output volume. For example, let's consider an input size of 32 by 32, a filter size of 5, a stride of 1, and a zero padding of 2. To compute the spatial size of the output volume, we can use the formula where the output size is equal to W minus F plus 2P all over S plus 1, where W is the input volume size, F is the receptive field size or the filter size, S is the stride, and P is the amount of zero padding. Plugging in the values, the output size would be 32 minus 5 plus 2 times 2 divided by 1 plus 1, which is equal to 32. So with an input size of 32 by 32, a filter size of 5, a stride of 1, and zero padding of 2, the output size remains 32 by 32. Using this formula, you can easily compute the output volume size for different configurations of input size, filter size, stride, and padding. Now for parameter sharing. Conv layers use parameter sharing to control the number of parameters. Instead of each neuron having its own set of weights, neurons within the same depth slice share weights. Notice that the parameter sharing assumption is relatively reasonable if detecting a horizontal edge is important at some location in the image. Detecting that edge should intuitively be useful at some other location as well due to the translationally invariant structure of images. This dramatically reduces the number of parameters, ensuring computational efficiency. For example, a conv layer with 96 filters of size 11 by 11 by 3 results in 34,944 parameters, which is 96 times 11 times 11 times 3, plus 96 biases. The convolutional operation in a conv layer can be optimized using matrix multiplication. Local regions of the input image are stretched into columns, forming a matrix where each column represents a receptive field. Similarly, the filter weights are stretched into rows, forming another matrix where each row represents a filter. Multiplying these two matrices using np ... efficiently performs the convolution. The resulting matrix is then reshaped back to its proper output dimensions. This method leverages efficient matrix multiplication libraries, but uses more memory. Now let's talk about the pooling layer. A pooling layer is commonly inserted between conv layers in a ConvNet to reduce the spatial size of the representation, thereby decreasing the number of parameters and computation in the network, which helps control overfitting. It operates independently on each depth slice of the input using the max operation, typically with filters of size 2 by 2 and a stride of 2, which reduces the input size by half along each spatial dimension. For example, a 224 by 224 by 64 input volume becomes 112 by 112 by 64 after pooling. Now, generally, while max pooling is most common, pooling can also be done using average pooling or L2 norm pooling. Max pooling has been found to be more effective in practice. During backpropagation, only the gradient of the maximum value is routed back, which simplifies the gradient computation. Some modern architectures propose eliminating pooling layers in favor of using conv layers with larger strides to reduce the representation size. This approach has shown benefits in training certain models like variational autoencoders, or VAEs, and generative adversarial networks, or GANs. Normalization layers are designed to mimic biological inhibition schemes and have largely fallen out of favor due to their minimal practical impact. Now let's talk about the fully connected layer. In a fully connected layer, each neuron connects to all activations from the previous layer. Their activations are computed through matrix multiplication, followed by a bias offset, similar to traditional neural networks. Before a fully connected layer can process the activations, it is often necessary to flatten the output of the previous layer, especially if it's a convolutional layer. A flattened layer converts the multidimensional output of the convolutional layer into a one-dimensional vector, making it compatible for the subsequent fully connected layer. This transformation ensures that every activation can be connected to each neuron in the fully connected layer, maintaining the dense connectivity required for further processing and learning. Now, let's talk about ConvNet architectures. ConvNets typically consist of three main layer types: convolutional, or conv, pooling, or pool, and fully connected, or FC layers. These layers are stacked together to form a complete ConvNet. ConvNet architectures usually follow this pattern, where n is the number of conv to ReLU layers before an optional pool layer, m is the number of such groups, and k is the number of FC to ReLU layers. Here are some examples. A simple linear classifier could go from input to fully connected. A basic ConvNet could go from input to conv to ReLU to FC. A common ConvNet would be input to conv to ReLU to pool times 2 to FC to ReLU to FC. A deeper ConvNet could be input to ConvNet to ReLU to ConvNet to ReLU to pool times 3 to FC times to ReLU times 2 to FC. Now let's talk about layer sizing patterns. The input size, or the input layer, should be divisible by 2 multiple times. For example, 32, 64, 96, 224, 384, or 512. The conv layers should use small filters, 3x3 or 5x5, with stride 1 and appropriate padding to preserve spatial dimensions. Now for pooling layers, they should use max pooling, which is most common, with 2x2 receptive fields and stride 2 to downsample the spatial dimensions. Now let's cover a few case studies of CNN architectures historically. First, LeNet, developed by Jan LeCun in the 1990s for digit recognition. It was key in pioneering the use of ConvNets for practical applications, like reading zip codes. Next is AlexNet, created by Alex Krzyzewski, Ilya Sutskever, and Geoff Hinton. It won the ImageNet ILS VRC Challenge in 2012, outperforming the runner-up significantly. And it introduced deeper and wider ConvNet structures with stacked conv layers. Now, ZFNet, which was developed by Matthew Zeeler and Rob Fergus. It won ILS VRC 2013, and it improved on AlexNet by tweaking hyperparameters, particularly in the middle convolutional layers. After that was GoogleNet, developed by Szegedy et al. From Google, which won ILS VRC 2014. It introduced the inception module to reduce the number of parameters significantly, and it replaced fully connected layers with average pooling at the top of the network. At the same time was the VGGNet, developed by Karen Simonian and Andrew Zisserman. It was runner-up in ILS VRC 2014, and it demonstrated the importance of depth in ConvNets with a simple and homogeneous architecture using 3x3 convolutions throughout. Despite high memory and parameter requirements, it showed excellent performance. After that was ResNet, developed by Kai-Ming He et al. It won ILS VRC 2015, and it introduced skip connections and heavy use of batch normalization. These skip connections enabled a direct flow of information, like features, from earlier layers to later layers, also aiding in preserving gradients and promoting better convergence. This helps mitigate the vanishing gradient problem, where gradients become extremely small as they're propagated backwards through many layers. With skip connections, gradients can flow directly through these shortcuts, allowing for better gradient flow during backpropagation. Batch normalization normalizes the inputs of each layer by adjusting and scaling the activations. It helps prevent internal covariate shift, where the distribution of each layer's inputs changes during training. This technique not only prevents vanishing or exploding gradients, but also allows for higher learning rates and reduces the dependence on careful parameter initialization. ResNet also eliminated fully connected layers at the end of the network, and it set a new standard for ConvNet performance and has become the default choice for many applications. These case studies highlight the evolution and improvements in ConvNet architectures, each building on previous innovations to achieve better performance and efficiency. Now for some practical advice. In most applications, use pre-trained models from ImageNet and fine-tune them for your data, rather than designing or training a ConvNet from scratch. This is called transfer learning, and we'll talk about it again near the end of the video. Now for some memory considerations. When designing ConvNets, be aware of the memory constraints, especially the sizes of intermediate volumes, parameters, and additional data like batches. To estimate memory usage, First, calculate the number of values and activations and gradients. Second, multiply by 4 bytes for floating point or 8 bytes for double precision. And third, convert to gigabytes by dividing by 1024 multiple times. Reducing the batch size can help fit the network into available memory. Now, how do we visualize what ConvNets learn? Several techniques have been developed to understand and visualize the features learned by convolutional networks, addressing the criticism that neural networks are not interpretable. First, layer activations. We can visualize network activations during the forward pass. Early activations are dense and blobby, becoming sparser and more localized as training progresses. This can reveal dead filters if activation maps are consistently 0. Second, we can also visualize weights. This is particularly effective for the first conv layer. Well-trained networks show smooth, organized filters. Noisy patterns indicate insufficient training or overfitting. Third, maximally activating images. We can identify images that activate a specific neuron the most, which helps us understand what features a neuron detects. Not all neurons have clear semantic meanings. They represent basis vectors in the image patch space. Fourth, Tessany embeddings. We can project high-dimensional CNN codes into 2D using Tessany, visualizing the similarity between images in the representation space. Similar images are placed near each other based on class and semantic features. The fifth thing we can do is occluding parts of the image. We can determine which parts of the image contribute to the classification by sliding an occluder over the image and plotting the class probability, and this can be visualized as a heat map showing the importance of different image regions. These techniques provide insights into how ConvNets process and understand visual information, making the learned features more interpretable. Now let's talk about transfer learning. In practice, training an entire convolutional neural network from scratch is uncommon due to the large dataset size required. Instead, like I said before, pre-training a ConvNet on a large dataset like ImageNet and using it for new tasks is more practical. There are 3 main strategies. First, using the ConvNet as a fixed feature extractor. We can pre-train a ConvNet on ImageNet and we can remove the last fully connected layer. And we will use the remaining ConvNet as a fixed feature extractor for the new dataset, producing CNN codes, training a linear classifier on these features finally, for example, SVM or softmax. The second thing we can do is fine-tuning the ConvNet. We can replace and retrain the classifier on top of the ConvNet, optionally fine-tuning the weights of the entire ConvNet or just the higher layers. Earlier layers contain generic features, and later layers are more specific to the original dataset. Third, pre-trained models. We can use pre-trained ConvNet models available from resources like Cafe's Model Zoo, and we can fine-tune these models for specific tasks. So how do you decide when and how to fine-tune? Deciding the transfer learning approach depends on the size and similarity of the new dataset to the original dataset like ImageNet. First, if you had a small and similar dataset, use a linear classifier in CNN codes to avoid overfitting. Second, if you had a large and similar dataset, fine-tune the entire network. And 3, if you had a small and different dataset, train a linear classifier, potentially from earlier layer activations, to capture more generic features. And finally, if you had a large and different dataset, fine-tune the entire network or train from scratch, starting with pre-trained weights. Now for some more practical tips. Let's talk about architecture constraints. When using pre-trained networks, you may be limited in modifying the architecture, but can handle different spatial sizes due to parameter sharing. Now for learning rates, use a smaller learning rate for fine-tuning convolutional network weights compared to training the new linear classifier to avoid distorting pre-trained weights too quickly. These strategies and tips make transfer learning a powerful approach, leveraging pre-trained ConvNets to achieve high performance on new tasks with limited data and computational resources. In conclusion, convolutional neural networks have revolutionized deep learning, particularly in computer vision, by efficiently processing and analyzing visual data. Throughout this video, we've explored CNN architectures, key layers, and practical applications, showcasing their unparalleled ability to recognize patterns and structures in images. While CNNs remain foundational, transformers are increasingly being used for visual tasks, offering exciting new possibilities. If you have any questions, leave a comment below. Like the video if you appreciated it, and subscribe to stay tuned for future videos, including an upcoming one on transformers. Thank you for watching. Cheers.